It's a pleasure to be back in IMPA once more, and especially to wish Maurício a happy birthday. This is the actual day of Mauricio's birthday. Very good. And, well, I guess I'll make a few remarks about my history with Maurício. When I was a grad student, just beginning, I had some beginning success on this closing lemma, which was Mauricio's interest. And he invited me here for, well, I guess I was about 23, something like that. And it was the beginning of my life as a mathematician. So Maurício is very responsible for that. And obviously he's responsible for many people here, their life as a mathematician. So I know the gratitude is focused in on Maurício from many directions. So what I'm going to talk about is some work. First of all, joint work. Conan Wu, who was an undergraduate at Toronto, where I've been for the last 5 years, and she's now at Princeton. But I suspect she will be traveling through IMPA. She's a great traveler at some point. And what I'm going to talk about, grew out of things that I was thinking about even before I met Maurício. So it's old stuff in many ways, but I hope you will find it of some interest. Now, there's I'll draw pictures if you don't have the slide to put up. Just 3 things. Right, that's one. Doesn't matter. There we go. All right. So cast yourself back to when you were first taking a course in ordinary differential equations. And as you begin the course, then you are presented with the fundamental theorem about existence and uniqueness of solutions of ordinary differential equations. And the standard result is that if you start with an ordinary differential equation, which is Lipschitz, then it will have solutions through any given initial condition, and that solution will be unique. Standard theorem. And then the standard example, which shows that you are not getting uniqueness, although you do get existence, when the differential equation is only continuous. The standard example is this visible or is it too small? Too small, right. Anyway, so the standard example is y prime. Okay, there we go. All right. The standard example at the top is just the square root of y. And you put a 2 out there to make things nice in terms of the formula. And this differential equation, the simplest standard example of this, has lots of solutions through a given initial condition. The initial condition being 0, and you can see the solution in darker, which runs along the axis for a while and then is quadratic. Okay, so this is a standard example. And you can look at this more generally, you can say, well, suppose that you've got a differential equation where this is in multivariables, and suppose that it has an initial condition at some, say, time t0, and you can look at all the solutions of the equation with this initial condition. And you can then imagine the graphs of them as in that, excuse me? Continuous, but not Lipschitz. And you can imagine all the solutions through the original initial condition. So this is at time t0. And then you can see where the solutions have come in y space after time t1. And you can look at this, and this is the funnel of all the solutions. That's a good name, because you imagine the solutions emerging from this point in some sort of a shape like smoke or a funnel. Yes?
More or less assuming that the only point where you have only is the initial point.
I'm just assuming that f is continuous. So these kinds of phenomena could be occurring everywhere, in principle.
Even in the funnel.
Yeah, right. So the funnel is not just a lot of curves that are disjoint from each other, but they might be intermingling. But if they do, they're tangent. Okay, so you get this picture of, I don't know what it's of, but lots of curves coming out of a point. But you look at the cross-section. That means that at time t1, you examine all the solutions in y space, which have started at t0 and have arrived at some points in y space at time t1, starting out from this initial point. So this is the cross-section of the funnel, starting out at the point y0, at time t0, getting up to time t1. And the standard theorem about this, in general, in this case, you can see what the cross-section is. It's just a segment. The standard theorem, due to Kneser, 1920 or something like this, is that this is compact and connected. It's a continuum. You make a reasonable assumption about the differential equation, say it has compact support. Otherwise, you could find solutions which were blowing up in finite time. So, yes, this is occurring where y is in Rn. Okay, so this is a system of equations. So you can look at this. All right, so this is a subset of Rn. And you can say, well, okay, it's a continuum, but is there anything else you can say about it? It's connected. Is it path connected? Is it convex? Originally, people thought it was probably a very simple set, but it's not. This can be interestingly horrible, the cross-section. And so what I was interested in doing was just trying to fool around and find out what kind of continua were possible. And I got some partial results. And I guess far from answering the question as to what are they. So if you say, let script k n be the collection of cross-sections for differential equations defined on Rn, continuous, starting out at some point, at some time. What is this collection? What's it look like? What are its properties? which continua belong to it. So there were two basic results at the time. If you look at this continuum in the plane, so it's a spiral which spirals toward a circle. All right, so that's a compact connected set in the plane. And this is not. Possible. And it's also not possible that it occurs in any dimension. Never occurs. All right. So that's one fact. The other fact was that anything nice, like a polyhedron, is surface, polyhedron with smooth faces. All right, so that's the type of example, type of result. Here was compact. Surface in Euclidean space. That is the question. Whether or not being a member of this is a topological property. We have not, I have not, nobody as far as I know has answered that question correctly, definitively. Suppose that you have A, which is in here, and suppose you have B homeomorphic to A. Is B a frontal section?
For the example you gave, that would be true without simple event.
Yeah, right. In general.
For example, you can realize any not in free space?
Yes. Easy. Let me give a sketch of why you can realize the circle. Then you'll see that this is just easy sort of differential topology thinking.
What's wrong with that?
What's wrong with what?
That one that does not.
Ah, right. What's wrong with it? Why can't you do it? That's your question, right? Well, suppose you could. Then you would find that you actually, you can look at the covering of it. And you see that as the spiral goes around, it goes around infinitely often. And you could find a differential equation which theoretically had compact support, and yet when you graphed the situation in 3 space, you would find an unbounded solution to it. That's what's wrong with this.
Can you repeat that?
Probably not, but I'll try. If you could do this, then you would find that you were able to, in finite time, that is t0 to t1, bounded, that you would be able to get this infinite number of twists in the spiral. And if you're graphing this, with, what do you call it, with like the covering space here, you would find that you got something which was unbounded in finite time using a vector field with compact support. Okay, so in a sense that's what's wrong with it. But here, I was just thinking on the walk up here, a question I don't know the answer to, which is not unique at all. Suppose that you imagine the rayed foliation of the solid torus. All right? So you've got this torus, and think of one leaf in that. That leaf is kind of like this, right? As it goes around the torus, it gets closer and closer to the surface of the torus. And so if you took the closure of that leaf, what you would have is something like this. And I suspect that the closure of that rayed leaf would not also be possible. But I've just thought of it on the way up, so I don't know.
Anything that's not locally connected?
Ah, now that's the next question, right. How bad can they be? Here is an answer. Yeah, surfaces are fine. Well, okay, let me be more precise. Suppose that you take any set in Rn such that A is compact, connected, and the complement is diffeomorphic, or even homeomorphic, to the complement of a point. Then A is one of these funnel sections. So just having a complement be homeomorphic to the complement of a point, your set can be absolutely awful. Right? You know this so-called bucket handle? It's like you see lots of curves. I can't draw the bucket handle, but it's a horrible continuum. But the complement of it is homeomorphic to the complement of a point. So it's not locally connected. It's just a mess. You can find other examples where there aren't even any arcs in the continuum. So it's horribly un-arcwise connected. So this is an example. But let me show you why the circle is, because that's easy. In the plane, you can make a vector field with the following solutions. So the vector field is identically horizontal to the left of this point and identically horizontal to the right. And the solutions are like those here, but you've just bumped them off. Right? That's not hard to do. Just bump this example off. Would you agree to that? This is an example in the plane. You can make the example in 3 space by just repeating this at sheets parallel to the blackboard. Right? So that would be easy. So you could imagine doing that. If your imagination is good, I think you better just point at it. Imagine that and then roll it up. Do you see what I mean? You've got this on the blackboard here. Just take that plane and roll it into a cylinder. So you would have other cylinders which were parallel to it, where the trajectories were just staying in those cylinders. Right? And so you would start out, you would move along the cylinder according to these, and you would come to the end of the cylinder, and you would have a circle. And that would be done in 3 space. Okay? So that shows that the circle does belong to this
Can you construct a logic circle?
yes. In 3 space. You say, so imagine your circle is smooth to begin with. So you can certainly construct an arc on that circle. Right? And then you just let the arc grow as it moves around the circle. I mean, that's no problem. You can do that with smooth. And then you come back and you've got almost the whole arc. And then you just let the 2 solutions, which are at the end points, merge. So instead of emerging, they merge together. Okay. But this question here, Conan and I realized that we don't even know the answer when A is a Jordan curve, or rather when B is. So is it true that every Jordan curve in the plane can be achieved like this? Okay, so I'll discuss that in a minute, what the issues are. But you might, and you should ask, what in the world does this have to do with dynamics? This is just someone off in the wilderness thinking, well, what was an interesting problem? But why study this? I mean, is there any... What is the doubt?
Yeah, I mean, it's not differential, it's not deep sheet, but it's still a dynamical system. So.
Oh, yeah, okay. You could say it's a dynamical system of sorts, but there's a better answer to this. The answer is that situations like this, with non-unique solutions, actually occur with partially hyperbolic dynamics. And so I mentioned this. Partially hyperbolic dynamics means that you have a diffeomorphism of a manifold, C infinity, and the derivative has a three-way splitting. Where the vectors in this space are expanded, the vectors in this space are contracted, and some neutral things happen in the center direction. And this is a lot of investigation goes on with these partially hyperbolic diffeomorphisms. However, this center direction, well, all three of the directions are just continuous in general, or Hurlder, of some Hurlder exponent less than 1. That's the situation here. These two, the EU and the ES, they do integrate to foliations. But the issue of the center bundle, does it integrate to a foliation, is a bit problematic. There are extreme examples, that is, where the degree of neutrality of this is pretty close to the degree of expansion or contraction. In other words, when I say neutral, I just mean it's somewhere between the EU and the S. Well, if it's too close to the EU, too close to the S, then this actually might not be integrable. But even if it's pretty neutral, Hertz, and Ures have an example. Okay, we can do the next slide, if you would. And if you can make it bigger and bigger. All right, that's pretty good. Oops. Well, anyway. All right. They have made examples in this partially hyperbolic situation where the center foliation is not such a great foliation, because although it's got leaves which are tangent to the EC direction, there's also curves. Their example, I should say, is in dimension 3. It's on a 3 torus, and so this has dimension 1, 1, and 1. And so the picture here is shown in, I think, that two-dimensional plane. But the point is that the foliation is not uniquely integrable. There are these rogue solutions to it. So the non-uniqueness is actually occurring in a smooth dynamical system. And their second example is showing that you don't even necessarily have an actual smooth leaves. That these leaves here, they have cusps along this curve. So this center foliation, which we're always typically assuming exists and is at least reasonable, pathological in some ways, in some sort of measure-theoretic ways, but at least has smooth leaves, is not necessarily true. We have this situation of bad, bad situations, non-unique integrability. So this occurs.
Look at it, look at it's only globally that.
It's only along a certain curve that it's bad. It's good elsewhere, but there's a bad curve. Now that's a good question. How much worse can such situations be? There exists in the book of Hartman on ordinary differential equations an example of an ordinary differential equation which has a non-unique solution at every point. And so I've tried many times to go through that example and understand it, but I haven't succeeded yet. Could that occur in smooth dynamical systems? That is, where it's not this non-unique integrability occurs everywhere. That would be interesting. All right, so I want to pose a few questions because I like questions, perhaps even better than answers. So these are sort of right. Okay. The example I just erased had in this picture here, this is occurring essentially in dimension 2. But what if you assumed that the unstable and the stable were large, but that C equals 1? So partially hyperbolic, but in higher dimensions. Then you have the conceivability of actually interesting topology on the non-uniqueness. You can ask in this situation, well, in their situation here, you can see that you're getting effectively the one-dimensional case where you get a segment of non-unique solutions. But could you get a circle? In other words, which kind of cross-section of their solution funnels in the partially hyperbolic case are possible? Okay, or other ones. That's one question. Here's another question. Suppose you're asking similar questions, but with plane fields instead of with vector fields or line fields. That's the stuff I was talking about in the beginning, is ordinary differential equations. But suppose you had say, a plane field P in Euclidean space. Say the planes had dimension 2 and you were in R4, something like that. So you imagine that you have a field of planes. Now typically your field of planes is not going to be integrable. But suppose that it's locally integrable and it's continuous. As locally integrable in the following sense. Through each point P, there is a disk everywhere tangent to the given plane field. So that's assuming locally that you have leaves, or at least disks, which are tangent to your given plane field. What is the theorem of Kneser in this situation? Kneser's theorem for ordinary differential equations says, okay, you've got this cross-section, you've got a funnel. Take a cross-section, you understand it a little bit. What's the corresponding situation for plane fields? Do you see the question? In other words, how does the pathology look in cross-section? That was one question. Another question that I wanted to point out. Yes?
What replaced, so before you were going from T0 to T1.
Right. Now, that's part of the question. How should you look at it? One way I can imagine to look at it in 3 space is that you take a cylinder which surrounds the point in which you're interested. Then you look at all possible disks tangent to your plane field through that point. And you look at how the disks cross the cylinder. And you get some kind of weird set that way. And you might like to describe it. That would be one way. But I'm not saying I have an answer to this. I just ask, what is the two-dimensional Kneser theorem? Kneser theorem for plane fields. Formulate it and prove it.
What are the examples that you know which are not product of one-dimensional example?
I know nothing.
You know nothing.
Right. But that's what I like about problems, is because you say something a bit vague, and then people invent the right theory for it. All right. Another problem is left over from... This has nothing to do with my talk, by the way. The next two problems are totally irrelevant to the talk, so can reset. The question in the wonderful paper by Maurício, the two-dimensional structural stability paper, concerns flows on two manifolds. But there is an issue about orientability. The theorem is completely proved when the surface in question is orientable. The theorem saying that the generic vector field is structurally stable. But what if the vector field is not? What if the surface is not orientable? That is an open question, except when the surface is a Klein-Bottle, the projective plane, and I think one more or two more non-orientable surfaces. But if the orientable surface has a big genus, non-orientable surface has a big genus, then it's an open question. So I wanted to point that out. That's probably an interesting, hard thesis for somebody, you graduate students who are here. All right, so here's the next question is something you could work on the airplane on the way back. It's this. This is a question Mo Hirsch showed to me. He says, suppose you take a smooth Jordan curve, maybe in the plane, but complicated, and you have a needle, and the needle has a fixed length, L. And the base and the tip of the needle are on the curve. And your goal is to slide this so that the length of the needle stays constant and the needle goes all the way through the curve and returns to the original. All right? You see the problem? Prove you can do it. A, for smooth Jordan curve in the plane, I don't know how to prove it even then. But if you succeed in that, well, then put the Jordan curve in 3 space. Now, you can see that if your curve is kind of tame like this, that's not a problem. But the issues will come up if it has parts like this, where you have to slide the needle down, move the needle to the new position, slide the needle back, right? Then the needle gets over here, and you bring the base of the needle back, and then you have to slide back, right? So you can see that this is a puzzle that maybe you can solve. Anyway, I've gone on several plane trips unsuccessfully. Okay, now back to the talk.
You have to start out with the position of the needle that only is on a small part of the curve, right? Because if you take a big dumbbell,
Yeah.
you put the needle in the middle, you can't.
Right. That's right. Then you would be totally stuck. Right. You have to start out at a reasonable place. Correct. And it's also obvious that if you fix the curve and you make the needle very short and the curve is smooth, then it's no problem. Just move it along. But so this is a medium-sized needle with ugly parts of the curve.
You state these questions.
Huh? Oh, it's just a question that was asked in the coffee room. It's
You don't know the status.
don't know the status. Neither does Mo. If the curve is not smooth, that is, it's got some ugliness to it, then there's a negative answer. That was, I'll remember his name in a few minutes. Well known to people here. Misarovich. Okay, now, back to this thing about Jordan curves. So, we realized we did not know the answer whether every Jordan curve in the plane, not smooth, is it true that it belongs to, i.e., is there a ordinary differential equation such that it has non-unique solutions, continuous equation, and after time 1, you've started at a point and you ended at the Jordan curve. So, not clear. Smooth, no problem. Here's the difference. Suppose that you, well, here's a proof picture. When the curve is ugly, but can be pierced at some point by either a straight line, that would be ideal, or by a curve of finite length. Suppose that you had a Jordan curve, ugly, but at least at one point it was okay. Then you would say, all right, I will now look, I will kind of open things up here, mentally, and consider, so I'm opening this up and looking at the complementary arc. The arc, the complement of an arc, is diffeomorphic to the complement of a point when you're in the plane. So I know I could find a differential equation, continuous, and it would have this funnel, and after time 1, it would come out and look like the arc. Right? I could do that. I know the general theorem. I can do that. And then I just say, well, okay, good. You got the arc. Now, gradually just close up this eye. And that's a proof. I mean, you have to write down all formulas and things like that, but it's not surprising. If you can pierce the curve nicely at some point, that's good. Now, this piercing is not always possible. The curve can be ugly at all points. And there are curves which are not pierceable at any point by arcs like this of finite length. And Conan and I proved that. And so, we just don't know. However, suppose we were willing to go up one dimension. Every Jordan curve in the plane can be achieved if you look at differential equations in one higher dimension. And this is not a completely shocking fact, because what you do is you say, well, okay, I've got this Jordan curve, and I think of it as the union of two arcs. Just arbitrarily divide the Jordan curve into two arcs. And I know I could get each arc individually. And you say, well, okay. Okay, so this is a diagram of what we do. We say, okay, start out at some point, and I'm imagining this occurring in 3 space. After a while, this point has developed itself into a segment. And we say, well, okay, now we have two planes in 3 space, parallel to each other. And in this plane, we let the, we do this by pieces. So in other words, we've developed it. It'd be better to draw the picture like this. So our first vector field differential equation has become 0 after a certain time. And then we say, okay, in this plane up here, we will let this point manage to get to the set A. And down here to the set B. Now at all times, we know that by Kneser's theorem, we have to have a connected set. And so we just drag along this line. And so we get A here, B there, and a straight line between them in 3 space. And then we say, well, okay, that's good. Now we just compress the line. And A comes down and B join each other to make the Jordan curve. So that's that same kind of construction yields a proof also that if you have any two funnel sections, then that implies that the union belongs to n plus 1. But we do not know in general, if you start with A and B, which are sections, that is A union B a section without going up, i.e. does the union belong here? Of course, we're assuming the union is not disconnected, that there's a common point. Okay, so that's some of the things that we did. We also wanted to ask ourselves about genericity, of the badness of a Jordan curve. So we wanted to make a statement like the generic Jordan curve in the plane is nowhere pierceable by arc of finite length. Just to show that that is exactly what I'm about to say. And then we realized that it wasn't so obvious what we meant by generic. We had an idea that there should be some topology on the space of Jordan curves, but what is it? Because you want the topology, if it's a metric topology, you want it to be complete. Otherwise, you're not saying anything interesting. So, thanks to Andy, who's here someplace, I suspect, and some other people, we came up with a definition, which is harder than we first thought it would be. But it's this. First of all, you may as well think of the sphere instead of the plane. And you may as well just say, well, I'm only interested in Jordan curves which separate the poles. Okay, so I'll just look at that collection of Jordan curves and try to put a good metric on it. And the metric is that you say, well, each of the two complementary domains in the sphere, there's associated to it a Riemann map. That is a mapping from the disk to the complementary domain, even when the curve is terrible. All right? And you can normalize it by saying the origin has to go to the pole and that it has to be, has to have a real derivative, real and positive derivative at the origin. So you can say, well, okay, you've got canonical parameterizations of the complementary domains. And then you say, well, I'll use them to give my metric. So you say, well, how close are two Jordan curves? Well, the answer is you take the two parameterizations and you ask how close those are. That's your metric. But we found one theorem which took some uncovering. So I mentioned the theorem. It's the kind of theorem you want to be true, and luckily it is. It's due to Rado. And it says that the parameterization of the complementary domain, let's call that R for Riemann mapping, R is a continuous function of the Jordan curve, or more precisely, parameterizations of the Jordan curve. And once you know that, then you can, well, I'll just draw a little picture of how you can say, well, this business about non-pierceability is a generic property. If you have this theorem, that's not too hard to do. Now, the Jordan curve. Okay, Jordan curves are homeomorphic images of the circle. So that's what I'm talking about, parameterized Jordan curve. Okay? Now, as I say, we looked and we asked people, and this turns out to be very nicely explained in a book which I had not known before, by Pomerenke. I don't know how many M's, I'm not sure of anything here. Something like this, called The Theory of Univalent Functions, or something like that. It's a nice book. So,
This topology is kind of strange because it's not invariant under conjugacy by homeomorphism to the sphere.
right. But it is a topology, and it makes this class of Jordan curves a complete metric space. So, it may not be the best, but it's something where we can say the word generic and have it mean something.
Is that the topology that you use to define continuous here is not good enough?
Say again?
I mean, you know what you have to say, the topology of Jordan curve.
Okay, let me, okay, here's what I mean. Continuous function of H, where H lies in the continuous functions from the circle into the sphere, where you put the usual C0 topology on this. You could try, but you would find that it wasn't complete, because this, your sequence could very well have non-one-to-one limits. Not good enough either. Right, Hausdorff metric would be good. Doesn't work. Because of this. Exactly. So you've got to avoid this. And this, the Riemann mapping, it hates this. It says you're getting these curves close together, your Riemann mappings are going nuts, right? So Riemann mapping is sensitive to this possible almost not one-to-oneness. Is it? We call it the welding topology because this is, you're welding one disk to another disk, and they use the word welding in this part of the world. Okay, so let's see what else. Oh, yes. What is the idea of making Jordan curves with bad pierceability? The idea is very simple. You say, okay, suppose that you've got a circle. You've got a point inside and a point outside. No problem. You can get from one to the other, piercing the circle, and your arc length is no problem. So you say the first step is that you will draw, instead of the circle, something very close to it in this weaker sense, which looks like this. Buttons on the circle. You say, okay. Still, it's easy to get from this point to that point. Then you say, let's draw a better picture of this part here. Okay, so one button. Okay, and so forth. You say, okay, let's erase this part here and draw in a kind of a channel. You think of this as a channel, but you draw in a channel which causes difficulty for a point, for a curve to get from here to there. It's going to cause, I don't know if I've drawn enough of these to be very convincing, it's going to cause longer arc length, right? And you can do that, obviously. You can take any smooth curve and you can approximate it by a curve which is going to have huge length necessary to join one point to another. And you use this kind of theorem here in the limit. So it's just a lot of epsilon over 2 to the k kind of arguments to realize that as soon as you get difficulty in joining 2 points, you can take it to infinity. So that's some of our results. Right, we're taking that clock to be accurate. So I think I will stop at that point.